Welcome back to another Earth is Our Home with Dr. Thomas Blaine. Today we're going to continue with how the climate engine works. So stay tuned. Welcome back to another Earth is Our Home with host Dr. Thomas Blaine. He's an associate professor with the Ohio State University Extension Program. We have been looking at a variety of different things involved with climate change and global warming. And this is going to be a continuation of how the climate engine works, as we had seen in the previous episode. Tom, it's a pleasure talking to you. I really learn a lot.
Well, it's a real privilege for me to be on here, and I want to thank you for having me and co-hosting. I think that we are covering a lot of good ground and hopefully answering a lot of questions people have about climate in general.
Well, I think so. You know, your discussion about the climate engine and how that affects the weather patterns, I think is very, very good.
Okay, as you can see, we're into June now. Basically, what we're doing now, this is part 5 of my entire video series. Last time, we went through a very basic model of Earth circulation, atmospheric circulation. We talked about cells of circulation and their results, which include the jet stream, the trade winds, high and low pressure systems, things like the prevailing westerlies that bring us our weather, things like that. We introduced all those things. But if you watch that, you could see it was an abstract model. Today, we have to introduce factors that make the climate model a lot more complicated. And the two major features are land features and Earth's tilt. They complicate the picture. For example, we showed the directions of winds at various latitudes caused by the uneven heating of the Earth, where the sun shines a lot more directly in the tropics than it does in the upper temperate zone in the northern hemisphere, what you call the lower temperate zone in the southern. The sun is very low near the polar regions, sometimes is not out at all in Arctic winter or Antarctic winter. And because of those changes, that those are a result of Earth's tilt, the climate model becomes a lot more complicated. So you might have looked on there and seen where prevailing winds blow at certain latitudes and realized, well, the wind doesn't blow like that here. And we're going to talk about why that is. We're also, if we have time today, and if we don't, it'll be the next time, why global temperatures have warmed so much more in the North Polar region than in the South Polar region. You know, we talk about global warming. It's been very uneven. The Earth's warmed a lot, as we saw in the earliest episodes. And I encourage folks to go back and watch those first 2 or 3 episodes on global warming trends. Also, we want to talk about the tendency of tropical storms and hurricanes to strike the Caribbean from the east and then subsequently hit the USA. We all get glued to our TV sets, don't we, in September at the height of hurricane season? But that brings to the question, why is it in September? Why don't we have hurricanes now in June? We don't see hurricanes coming across. Most people simply don't know the answers to those questions. We started with basic concepts of circulation. Now, the basic concept is the concept of a Hadley cell, where the Earth receives radiation from the sun, where the sun is standing directly overhead. It warms more there in that location. We also know from physics, I'm sure you learned in school, you got a package of warm air and a package of cold air. The warm air will rise and the cold air will rush in. On the surface, that's called wind. So if you're standing on the equator, roughly at about the time of the equinox, you're going to get winds coming into the equator from both the north and the south. And in the middle, you're going to have rising air. Rising air means the pressure is low. That's low atmospheric pressure. Air, as it rises, cools and condenses. When it reaches the top of the troposphere, it's got to go either north or south. No place else for it to go. So some goes north. That's the northern Hadley cell. It gets cold as it stays up high. If you've ever flown, you look at the weather information. You took off from an airport where it was 90 degrees. You're at 35,000 feet. And you see, my goodness, it's negative 47 outside. It's always cold up there. That's caused by lower atmospheric pressures high up, and cold air then ultimately has to sink. And it sinks at about 30 degrees north, 30 degrees south. Then when it plunges and hits planet Earth, some of it goes back toward the equator and completes the Hadley cell. Others go the other way. And here's a diagram of that. So we see outside of the Earth there, the Hadley cell, rising air that's warm near the equator. Then it moves away from the equator. And then when it gets so cold, it finally plummets to Earth at about 30 degrees north and 30 degrees south. This repeats itself at 30 degrees, and you have a Ferrel cell where that air sinking plunges down, then some of it comes back toward the equator in the Hadley cell, but other portions of that air move north in the northern hemisphere, south in the southern hemisphere, and then as it does, it warms along the surface, then it rises and then closes back, and that's a Ferrel cell. We live inside a Ferrel cell. Ohio, Columbus is about 40 degrees north latitude and everything. And the polar cell is next from 60 degrees to the pole. But again, this time of year, for example, the sun is not shining directly overhead of the equator. The sun is shining now overhead of about 19 or 20 degrees north. And on the day of the solstice coming up here in just a few weeks, it'll be shining directly overhead the Tropic of Cancer, which is 23 degrees north, almost up to that 30 degrees north. What that means is the Hadley cell moves up. It moves up and brings with it the very warm air of the Hadley cell. And the Ferrel cell then is forced to move on up. The polar cell is forced to move up or shrink. And this is why we have summer. We're in the warm part of the year. It's partly because those cells are moving, and they're moving because the sun does not shine directly overhead of the equator year round. Right now, it's shining directly overhead, just about almost as far north as it will get. Here's another graph I found to try to explain this a little bit differently. Again, if you look out over past where the planet is, you'll see those cells of circulation. If you look way over to the right where it says equator and the Atlantic Ocean, where it says the word equator, you'll look just above that out there is a Hadley cell. Look at the cell of circulation. It's flowing toward the equator on the surface in both the north and the southern hemisphere. When those get together, they rise and then flow back away from the equator. Those are two Hadley cells. Then the Ferrel cell, if you go on up, and then if you go on down in the southern hemisphere, and then up at the top, you have the polar cell. And they put these on each side of the planet just for clarification. But basically, there are six cells of circulation on planet Earth. Two Hadley cells, one just north of the equator, one just south. Two Ferrel cells. We live in a Ferrel cell in the northern hemisphere, and then a polar cell. You also see that these winds, as they rush back toward the equator or move toward the pole, they get bent. And they get bent not just to go south or north, they get bent to flow in other ways because of the Earth's rotation. The Earth's rotation causes the winds near the equator to come more out of the east, not just straight north to south toward the equator in the north, or not just straight south to north toward the equator in the south. They bend, and those are called trade winds. Then you come up to where we are. If you look in the middle part of the United States, inside a Ferrell cell, which is where we are, notice the westerlies. So when you look at the weather map, you see that we get most of our weather from the west. You know, you look at the weather map, you see those fronts coming. They almost invariably come across from the west. We get weather from Minnesota, Iowa, down through Missouri, Arkansas. They come from the west toward the east. That's because we're in a Ferrell cell where we have prevailing westerly. So I thought this graph might help.
Does land mass affect the direction and the flow of the wind?
Absolutely. And that's what we're going to talk about right now. So let's keep on this, since you mentioned that like that. Let's keep on here. And let's say you're standing on a beach on the eastern coast of the United States on a hot, sunny summer afternoon. Who doesn't like to go to Virginia Beach or the Carolina beaches in the summer? As you can see, according to this map, here in Ohio, for example, the winds would probably be mostly out of the west. But let's say you're standing on that beach at Virginia Beach. What happens is the sun heats up the land really quickly. Land heats quickly. If the sun comes out, the land heats up like that. But water doesn't. It's a thing you learn in physics, but I think you're aware of it. If you put water on the stove, turn the high heat on, it can take a long time for that water to boil. Water, because of the way that it's structured physically, the atoms and molecules and so forth, water's hard to warm and it's hard to cool. So, and people intrinsically know that. Like if you're standing on the beach on a real hot day, you know that the water's liable to still be quite cold. All right. But the sand is burning your feet. So why is it the sand's up over 100 degrees, but the Atlantic Ocean never gets over 100 degrees? It just doesn't happen. And yet that sand burns your feet. You jump in the water's not going to burn you. That has huge implications for weather, because what happens is, as we've said before, when you've got a packet of air here and a packet of air here, and this one's warm and this one's cool, they won't sit there. The warm air will rise. So the air over land rises, leaving kind of a vacuum. Nature abhors a vacuum. So the cold air rushes in to fill it. The cold air rushes in. So if you're standing on the beach in the Carolinas on a hot, sunny day, the wind is not out of the west. It is not out of the west because you got rising air coming in off the ocean. It's out of the east. The winds come out of the east. And because the ocean's so big and the continent's so big, those winds can override the tendency of the prevailing westerlies that we learned in the climate engine. They can override that. And you might be 150 miles inland and the wind's still out of the east because that wind gained momentum. Let's do a thought experiment. So if you're standing on the southern coast of Mississippi, Alabama, right down there in the Gulf of Mexico, and that's beautiful country down there, beautiful beaches. According to this, you should be in the doldrums. You shouldn't be in any real windy pattern because the air's moving away from you in both directions. Notice if you're in Alabama or Mississippi down along the coast, some of that air is flowing like the westerlies are going up and out, whereas the trade winds are going down and out. So the air's moving away from you. So you should be in a high pressure system. You should be in the middle of a high pressure system where there's no wind. No wind at all. Okay. But what happens? The land there, the beach, land, the cities, the towns, they heat up. They heat up rapidly. Does the Gulf heat up? Not rapidly at all. It takes months, okay, for the Gulf of Mexico to heat up. So the air over the land in Alabama, Louisiana, and so forth is rising. It rises. And again, the air from the Gulf gets sucked in. So if you're standing down there along the Gulf Coast looking south, the wind's coming onshore. But that's not what we see in the graphic. We don't see that in the grid. It doesn't look like wind is blowing onshore in Alabama. And based on the global climate model, the wind should not be coming at you from the Gulf, from the south. But it is. Okay, let's say you're standing on the south shore of Lake Erie here in Ohio, beautiful warm summer day, and you're standing near a beach, you're on a beach at Cedar Point or somewhere near Cedar Point. What does the global circulation indicate? Our winds come out of the west. But it doesn't work like that. On a hot day, the air over top of Sandusky and those other places, Fort Clinton, it's rising, okay, because it's very warm. Cool air over the lake rushes in. That means the wind's out of the north. So believe it or not, you have days where on the south shore of Lake Erie in Ohio, the wind's coming out of the north. And if you crossed over the lake to the other side, the wind would be coming out of the south for the very same reason. Okay? Now, winds blowing like that in all these directions cause the atmospheric pressure to change. And that's why we get centers of high pressure and low pressure. So I'm going to summarize that. The simple model that we had before does not take into account what we call microclimates. A microclimate, as opposed to the macro, the big picture, was where we had a Hadley cell. That's a macro phenomenon. The Hadley cell is huge. It goes from typically from the equator all the way up to 30 degrees. But a microclimate is something in and around a feature like where landmass comes in contact with water. These are microclimates, and they change the flow. So we have some examples. I think we've done some of those. Where would you expect the wind to come from on a hot day near a beach? And well, the Carolinas, again, we would anticipate a westerly flow, but we have an easterly flow. The Gulf Coast, we would expect not much flow at all out of the doldrums, but we would get a flow out of the south because of the Gulf. Oh, western coast of North Africa. Look at North Africa. The air, typically there, North Africa, you got the trade winds, should be blowing out across there, but imagine it's a hot day out there and the ocean is cold or cool. It can't warm up very fast. Again, the air over the west coast of Africa would rise and it would be filled in by air from the west. And sure enough, you would get a westerly flow, which runs contrary to our simple model. North coast of Ohio, we did that. We expect a westerly flow, but on a hot summer day, you're going to get a southerly flow. Some of these go against the global circulation model, but a lot of them go with the circulation model. Let's see if we can find something that goes with the circulation of the warm model. If you look at California, so let's say you're standing over on a beach overlooking the Pacific Ocean in California or Oregon or something like that, and it warms up the land, the air rises, wind's going to rush in from the west. So that reinforces the flow out there. There are a lot of places where it reinforces the flow, but there are a lot of places where it runs contrary to the flow. Okay, so basically these are called microclimates, and they're very important in evaluating what happens. Mountains do it even more, because if you got a large mountain, Patrick, the air is going to be very cold. Mount Kilimanjaro is on the equator. We expect to have hot temperatures near the equator, right? But Kilimanjaro's got snow on top of it. The Himalayas, many of the Himalayan peaks are in the tropics where it should be hot, but there's snow and it rarely gets above freezing in many parts of the Himalayas because of the adiabatic cooling. As air rises, it cools down. And all these things play a major role in the development of high and low pressure systems, which play a major role in determining the weather and therefore climate. So this simple model that we predicted here, that we talked about, that generates the jet streams and the flow of air around the planet, is a simple model. It's the model that would exist if we didn't have microclimates. Land features like mountains, just the existence of land itself, low-lying land areas where the temperature heats up more rapidly, mountainous area where the temperature cools down. It reverses a lot of these wind flows, and the irregularity of the heating. If you want to think about why is our climate so interesting and chaotic, and why do we get high pressure systems, low pressure systems develop, they tend to develop for reasons of basic global circulation and become a lot more complicated because of the presence of land masses. Let me show you one thing that I'm talking about here. If you look at the Hadley cell, all right, 30 degrees north, way out to the right, you've got sinking air. See how that air's sinking? Anytime you have sinking air, that's a high pressure system. As the air comes down, there's more of Earth's atmosphere sitting on top of it. So the pressure builds. That's high pressure. High pressure is associated with dry weather because there's no water vapor high up in the atmosphere. The water on planet Earth is on the surface. In order to get water up into the atmosphere, it has to be carried there from the surface. So if you look where the cells come together and the air's rising, that air's juiced because it's carrying all that water from the surface of planet Earth. And as it goes up, it cools and the water in it condenses and it rains. If you look at 30 degrees north and 30 degrees south, sinking air. So you got low pressure. You tend to have low pressure centers where you have rising air. So where the Hadley cells come together, where the Ferrel and the polar cell comes together, you tend to have a lot of rain because you got rising air. But where you have sinking air, where the Hadley cell comes together with the Ferrel cell, about 30 degrees north latitude, sinking air means dry air and a high pressure system. This is why a lot of times in the summer, the sinking air that we get over in the North Atlantic Ocean causes a huge high pressure. It's called the Bermuda High, and it sits out there in the Atlantic Ocean. and it pretty much blocks a lot of storms. And that's why we have August is not only hot and humid, but it tends to be a time that's prone to drought here in the United States because the Bermuda High is dominating downward sinking air that just doesn't have the rain in it. But again, microclimate changes bring us rain. Microclimate changes bring us rain. As I told you, if you're looking here and you see, my goodness, if we've got that big high pressure system, how do we keep from getting droughts in July and August? Well, because of microclimates, because the air will heat the water locally over portions of the Gulf. That hot air will rise. As it rises, you get condensation. It forms clouds. More and more moisture gets in. You went from a nice sunny day to one where there's thunderheads, cumulonimbus, and boom, they unleash huge amounts of rainfall, life-giving rainfall. That's why we get a lot of rain in the summer for our crops in the east. But if you go out west at the same latitude, compare Arizona or New Mexico to Alabama. Alabama gets a lot of rain in the summer and has great agriculture. Arizona doesn't, because south of Arizona, you don't have the Gulf of Mexico doing its thing.
Hey, we're talking with Dr. Thomas Blaine. He's an associate professor with the Ohio State University Extension Office. Tom, thank you.